Here's a handout or a worksheet that we usually do in in-person class on paper, but now I've put it in the big homework file. It's right after the chapter 1.1 lecture text. So we're taking an intuitive approach here, and it's okay to eyeball values or just kind of give a number that seems reasonable. You don't have to do any real calculations for this worksheet. So what would you say the limit of e to the x as x goes to 2 is? So here I've got some values with x approaching 2 from below and from above. So what value do you think should go right here? Here's a nice polynomial as x goes to 1.6. Here we've got x values approaching 1.6 from below, approaching 1.6 from above. Now I'm not claiming that you get to divide by 0 here like we did with the difference quotient, but in some of these graphs we do, or in some of these tables we do, and some we don't. Does it make sense to average this number and that number? You got to think about things like that. Here's another nice polynomial, 1 minus x squared, as x goes to 0. And the interesting thing here, as I point out, is that as x approaches 0 from the negative side, these values are growing. And as x approaches 0 from the positive side, kind of going from the last row of the table upward, these values are growing. So what number do you think should go right here? Do you get a sensible answer if you plug 0 in there? Is that the answer you get if you average this number and that number? Or what if you put another 0 in here and there, get new numbers there? If you average those two, will you get the number that actually should go here? That's an interesting question, and we'll see that again graphically. So here, as you get close to 0, the y values keep increasing. As you get close to 0, the y values keep increasing, which is different than what was happening here. As you get close to our central value, here the y values are growing towards 0 from the negative side. As you go closer to our x central value here, the numbers are falling from positive towards slightly negative. So they're going in different directions, this way and that way. But here they're going in the same direction. Here's an interesting function, absolute value of x over x. What's the limit of that as x goes to 0? It's pretty obvious what you get if you average these two, but is that what you should get? Remember, we're saying what is the destination of the y values as x goes to 0 from the negative side? If you just saw this first part of the table, what would you say the destination was? If you just saw this part of the table, what would you say the destination of the y values was as x goes to 0? And if those two destinations don't match, well, what does the definition of limit tell us? I like this function because it's a lot like the function called sine, spelled S-I-G-N rather than S-I-N-E, which is a really handy function in some parts of math. And here's a graph of what it looks like. This is absolute value of x over x. It has no filled in dot here. The sine function, S-I-G-N, has a filled in dot at the origin. Here's another puzzle for us. What's the limit of the difference quotient for e to the x at x equals 2? So here's how we would write that. And we do get to divide by 0 at x equals 2. What number should go here? What do you think? There it is in kind of more common math notation. And then this one's really interesting. Instead of difference quotient of e to the x, this is difference quotient of the cube root of x as x goes to 0. So what's happening with the y values here as x gets close to 0 from the negative side? What about with the y values here as x gets close to 0 from the positive side? Can you just average these two? What would happen if you took another step and put another 0 here and another 0 there? This is an interesting table to analyze. What do you have to multiply 100 by to get 464? You multiply by about 4.64, right? Multiply 100 by about 4.64. What do you multiply 21 by to get 100? Something between 4 and 5. What do you multiply 4.64 by to get 21? Something between 4 and 5. What do you multiply 464 by to get 2,100 something? Something between 4 and 5. Seems like a trend. So what will happen if you keep putting more zeros in here? What will happen to the related number? So I'll let you think about that. Here's a graph of cube root of x. You know, we're talking about a difference quotient here, and difference quotients are related to derivatives. What does it look like the derivative is right here at 0? And here's a graph of the difference quotient. What does that seem like it's doing? So that's a bunch of stuff from tables. And then I also have a bunch of graphs that capture pretty much every case we might be interested in. And remember, this is in the big homework file, so you can go download this, find this page, print out this page if you want to, and write your answer to each of these. And then I've got the answer key here. I'll just leave it here. You can screenshot it if you want to from the video, or you can go see that file. So there's a lot of stuff to think about there, and that's our kind of table and graphical introduction to limits. And then the next thing is the homework. And in summer 2020, we're skipping the evaluation column because it doesn't work so well for all this stuff.